Okay, this video is going to help with this project, modeling energy changes in the thermochemical equations chapter. So let's take a closer look at the student guide and then understand exactly what's being asked. I'm going to complete this with an example equation, a chemical reaction, and then you can apply what I did in the steps to the actual one in the student guide to help you write up what you need to submit. So this is talking about reactions. One thing that we need to know is we need to understand how to write chemical formulas, how to balance equations, and I'll show you a quick review of that if you don't know how to. And understanding that energy is transferred in between making products out of reactants. So we classify reactions as either exothermic processes or endothermic processes. It talks about this in the background information. And so to determine if an equation is or a chemical reaction is exothermic or endothermic, we at the end decide there's energy that's being released on the product side after I've recombined bonds, or endothermic where I have more energy inputted on the reactant side to break bonds, to restructure them later. Okay, so we'll talk about those words exothermic and endothermic. Ultimately, you need to decide if the reaction that they ask you about in this activity is classified under exothermic or endothermic and have a value to prove it, and then make a graph. So let's scroll just to prep yourself. What should you be creating like in a document to be able to submit to the teacher? You're going to need to have a spot where you tell me your overall balanced chemical reaction. Your reaction deals with propane and it combining with oxygen in a combustion reaction. Okay, so I've got it up here in this little video. Propane plus oxygen yields or makes what two products? You won't have to do anything with this table. You are going to need to make a space where you fill in the substance, and then the enthalpy of formation of reactants and products will go here. You have table 3, where we have a total enthalpy amount, and you then are going to classify it as exo or endothermic. You could do these steps in a different way after you see how I write it out on my paper. I would be fine if you submitted it like that. And then in the space, we're going to make a graph. If you have to hand draw that and then take a picture to submit it, that would be fine, or you can use something to help you create that. So let's play this. So here's the actual problem that you've been proposed with. Propane plus oxygen is yielding what products? It talks about that in the preparing of the project. I'm going to use the example of using methane and oxygen. It is going to be a similar reaction. It's a combustion reaction. In a combustion reaction, we make two things. We make carbon dioxide gas and we make water. Below, I'm going to show you how to set up how to balance the chemical reaction. If you don't do this step, then you're not going to be able to have your calculations correct towards the end. So I've made a little T-chart, and we're going to be looking at what coefficients I might need to place in front of these reactants and products so that all my carbon atoms on the left side also equal the carbon on the right side. You're going to be doing that with propane plus oxygen. So you may need to Google or look up the chemical formula for propane if you are uncertain how to come up with it. Okay, so let's watch this video. So I set up this chart. Start by counting how many carbons, hydrogens, and oxygens you have on both sides. And then we have to play around a little bit with it to see what coefficients we can place in front of these so that I get balanced or equal numbers of carbons, hydrogens, and oxygens on both sides. So I'm starting to count up, and I use the little subscripts right now to tell me how many atoms of each of those I have on the left, and then how many I have on my product side. I've got carbons are equal so far, but I can see that I have a deficiency in the number of hydrogens, and I have too many oxygens on this side. So how can I start to balance these hydrogens? If I place a coefficient of a 2 in front of the water, and I multiply 2 times 2, that gives me 4 hydrogen atoms. Now both sides have the same amount. Over here though, let me pause. When I place that coefficient in front, that changed the number of oxygens that I have. I have now 2 oxygens in the water and 2 oxygens in the carbon dioxide. So I need to make my oxygens over here on the reactant side balance and match that 4. So how do I do that? I place a coefficient in front of the oxygen there. 2 times 2 is 4, and all of my numbers are all equal. So I have a balanced reaction. The 1 coefficient you could place in front of your methane and your carbon dioxide, but typically we don't see a 1 there because it's understood that 1s are known values if you see a molecular formula there. Okay, so let's move over to the equation, the chemical reaction that you're working with, which is propane plus oxygen. It's also a combustion reaction, so use what I did over here. What would my products be? I'm pausing, letting you have a chance to see if you can figure it out. They're also going to yield water and carbon dioxide. So I'm going to give you a little help here. Here's the formula for propane, C3H8 plus oxygen. Oxygen is a diatomic molecule, so that's going to be O2, yields or arrow, water and carbon dioxide. At this point, I want you to pause and see if you can set up one of those charts so that you can get the carbons balanced, the hydrogens balanced, and the oxygens balanced. Without this step, our calculations for enthalpy are not going to be accurate. So I would say pause the video here. I'm going to give you a minute to work and then unpause, and I will check your coefficients with you. And then we're going to move on to the actual part of calculating enthalpy. All right, balanced equation. You should have a coefficient of 1 in front of the propane. In front of the oxygen, there's going to be a coefficient of 5. Over here, we're going to have 3 carbon dioxide. And in the final spot, we're going to have 4 water molecules. So now that you've got a balanced equation, let's move on to what our overall goal is and understanding the difference between exothermic and endothermic. So it takes me a minute to shuffle my paper a bit. So we talked a little bit about why reactions are doing one thing or the other. They're either consuming or requiring a lot of energy on the front end to break bonds, or they're yielding and making a lot of energy that's released at the end of the reaction and giving off that energy in different forms. It could be heat, it could be light, it could be some other things. So we are going to see the symbol. This lab looks really tricky because this part looks, when you glance at it, really complicated. But let's understand what just some of these symbols mean, all right? The delta H is a symbol for enthalpy. That RXN was reaction, okay? So that stands for the enthalpy of the reaction. And then over here, this, I think it's called sigma. This just means that I'm making the sum of. So I'm going to be calculating the enthalpy of formation of the products, and I'm going to be adding those. This symbol just means I'm going to be adding the products values together, and then I'm going to be subtracting the sum of the enthalpy heat of formation of the reactants. I think I just said heat, but I didn't need to do heat. So we're basically going to do a math problem. All this means is I'm going to get an answer, I'm going to take a value of the products, I'm subtracting the value that I get for the reactants. And for this, we're going to be using this table of known values. Okay, so let's keep on going. When you get an answer to this equation, if you end up with a negative value, that's going to give you the indication that that reaction is exothermic. More energy is being released. If your value is positive, that would be an endothermic reaction. There's more energy that's being required on the front end of the reactants to break the bonds. Okay, so here I'm just kind of restating what this equation was here. To complete this equation, you have to multiply the enthalpy values by coefficients that we just did in the balanced equation. So that's why that part was important. I'm showing you with my example problem. This is not the one that you're going to write up in your lab report. You're going to do the math for that one. So in my problem, let me pause. as you can't see, I used methane, the combustion of methane. And so I start with my products, which are carbon dioxide and water. And it's going to show you, I'm going to point that I don't have any coefficients in front of the carbon dioxide, and I have 2 in front of the water. Okay. And then over on this side of my reactants, there's my methane and then my oxygen. So I just kind of wrote those above. All right, right here, these values, the enthalpy of the reaction is again, you get those from the little chart here. So I had to, you can find carbon dioxide, okay? And that number is the exact value that's in this chart because there's no coefficients in front of the carbon dioxide. So negative 393.51. Okay, and I'm adding that, again, this sign here means the sum of, I'm adding it, I take the 2 coefficient from the water, and then I'm using water's value from this chart, which is negative 241.82. All right, and then I bracketed that off. That's going to give me a number, might be a positive value, and it might be a negative value. So make sure you're carrying those down, and that will determine whether you get the accurate answer or not. For methane was an example that I chose to do, so I had to look up that value. That one is not one you're going to see on this chart. And the other thing that could be a little tricky is for oxygen. Oxygen's value is 0. It is a stable form, so that 0 value is just assumed because oxygen is a diatomic molecule. You're going to need this value in your example because you're also using oxygen when it combusts with propane. All right, let me play this part. So again, I got those values, the coefficients from my balanced equation. I'm just going to then take my 2 times this number. I'm just showing you where to get the numbers from. Guess I could hurry that along. Type this into your calculator. Again, ultimately, we're just taking a value for the products and we're subtracting a value from the reactants. And then we're getting an overall answer, all right, in kilojoules per mole. So this negative 802.34 is a negative value. And so come back up here. If my value is negative, it is an exothermic reaction. And so that's how I determine that overall more energy is being released in this equation. Most combustion ones are, right? That negative value. So let's take a closer look at the one that you're going to need to do, right? If you've got your paper out, you've got your balanced reaction, now it's going to be your turn. And you're going to use table A values. Again, we're going to do the products come first and then the reactants over here. So you can double check and make sure that you've got the right coefficients in your balanced equation. And I'm going to show you how I fill in this first box and then see if you can do the second box for the reactants and then calculate your answer. So I'm using the value for the carbon dioxide. I've got a coefficient of a 3, so I'm going to be multiplying those together. It's negative 393.51. And then I'm going to be adding the water's value. Water's enthalpy of formation value is negative 241.82. So 4 times that value there. And then just use your calculator to come up with an overall number. And then I want you to try to look up the values and figure out for your propane and oxygen. Remember, oxygen's that stable diatomic molecule. That value is going to be 0. You won't find that one in the table. This is the part where you can go back in and fill the values in. Let me pause. Into these spaces. These are your reactants and products. These are the values you calculated. Here is your overall totals, right? These values from these 2 boxes. Here's the answer to the reaction, and you deciding if it's endothermic or exothermic. And again, that depends on if the value is positive or if it's negative. Your final thing is to make a graph, okay? So for your graph, you can use the same title. You want to make sure that you provide labels for your axes. I use the title energy graph for the combustion of propane. On my y-axis, I have energy in kilojoules per mole. I have 0 all the way down to negative 2,500. And then on the x-axis, I have the reaction just as it's progressing. I went ahead and placed, based on the value you should have gotten for your reactants here, I went ahead and drew a corresponding line. That's where my equation or chemical reaction started. You're going to draw and connect a line all the way down here to our finished products. So once you determine the value of the products, you will know where to kind of estimate where that is on the y-axis, make a flat line kind of like I did for reactants, and then label it. Products. And final part would be, after you've got your graph, just kind of giving me a summary of, let me see if I can move this bar. Last thing I want you to do is overall, what did you determine about this reaction? Was it endothermic? Was it exothermic? How did you know? What is an endothermic reaction? What is an exothermic reaction? And that's it. Hopefully this was helpful. Try your best. Try to get your math correct. I'll look over it, and if you're stuck on a step, you can always message me to let me know. Good luck.